so today we're very happy to have Daniel Robbins from Albany, who is going to tell us about decomposition, orbifolds, quantum symmetries, and anomalies. Please, Daniel, take it away.
Thank you. Yeah. So it's the usual, title formed of a collection of random terms, but really, it's basically about a bunch of work I've been doing over the past couple of years. So a paper a couple of years ago with my student Thomas van der Meulen, and then 4 papers and counting together with Eric Sharp from this year, where we're really starting to uncover a fairly interesting structure. At the end of the day, we may or may not be getting anything really new. We're not getting new constructions exactly, but I want to claim that we've got sort of new ways of thinking of anomalies and how they fit together when you gauge things, and in particular in the presence of trivially acting symmetries. So and I also just want to say, with all of this, my student Thomas has put in a lot of work, and he's on the market this year. So if you enjoy the story we're telling, then consider keeping an eye out for his applications. All right, so I want to talk about two-dimensional CFTs and global symmetries and taking orbifolds, so basically gauging those symmetries. This is an old story, of course. A slightly more modern way to think about these things, I would claim, is through the language of topological defect lines. So in this picture, any global symmetry, so if you've got a global symmetry group gamma, any given element G of gamma, you can think of G, the action of that group on your theory in terms of some line operator G. So if you've got the cylinder here, you've got some state coming in from below. If you put that line around the cylinder and then fuse it down here, you just get the action of G on that state. These lines are topological, so the corresponding line operators commute with the stress tensor, and that means we can freely deform them around without changing the value of any correlation functions. A couple other facts. So you can think of, if you circle some local operator by one of these lines, that just tells you how the symmetry acts on your local operator. If you reverse the orientation of your line, it's basically just inverting the symmetry element, the group element. So these topological defect lines can meet at junctions, and at any possible junction, there will be some Hilbert space worth of operators that you could insert at that junction. So for instance, you could have a line just coming out of one point. So the operators you could insert at that point would be what we would normally call G twisted sector Hilbert space operators. And again, you can think of that in terms of the cylinder. Now the line would be going the vertical direction. And so a state, which would be on the spatial slice of the cylinder, is only periodic up to the action of G. And if you can formally map that cylinder to the plane, you'll get a picture like this. You can also have multiple lines going into a junction, a picture like this. So here I've got lines G1, G2, and G3. So there'll be some junction there. And again, I'll just label the Hilbert space with the lines coming in, or in this case, going out. And the order matters, the order that the lines are in. So I put a little X here to indicate, that's the last guy. I'm going to go counterclockwise around my junction and end at the G3 line. So this will be the HG1, G2, G3 Hilbert space. Different cyclic orderings are isomorphic Hilbert spaces, but it's not necessarily canonical. So we should mark things when we're being careful, but I won't always be careful in this talk. And I should say most of what I learned about this way of thinking about things, I learned from this very nice paper from a few years ago by Chang, Lin, Xiao, Wang, and Yin. All right, so when you got these lines, you got lines and operators at junctions and everything. So in this language, your CFT is, as usual with a quantum field theory, it's some gadget that, takes correlation, some sort of correlation function gives you a number. In this case, our correlation functions are going to correspond to these decorated pictures of Riemann surfaces with lines and operators everywhere. So again, these blue lines are topological, so we can move them around without changing the correlation function, as long as we don't pass through an operator. But the vertices are generically, they're nailed down. The exception is sometimes you'll find that in your junction Hilbert space, you may have some weight zero states. In that case, if you put one of those weight 0 operators at that junction, then that does commute again with the stress tensor and so on. And then in that case, you can move that junction around as well. So those are called topological junctions. And that's pretty special. So for the case of sort of ordinary group symmetries, then that act effectively, then the only way you can have a weight 0 operator that can live at a given junction is if the product of lines around that junction is the identity. And in that case, there's exactly a one-dimensional vector space worth of operators of weight 0 that you could put at the junction. And so, pick a basis vector there, and it's basically sort of an identity operator for that particular type of junction. Okay. We're going to talk a lot more about anomalies a little later, but for now, let me just say that as long as your group is not anomalous, then you can also resolve junctions. So I could take a 4 junction and split it into 2 3 junctions, like in this little picture down here. And as long as there's no, well, I can always do that, but if there's no anomaly, then I can do it in different ways and they'll agree, essentially. All right, so another step I need to kind of define before we start talking about gauging these symmetries and doing orbifolds is what I'll call partial traces, so ZG, H. If you've worked with orbifolds before, you of course are familiar with these objects, though maybe not in this precise language. Often they're talked about in more of a Hilbert space language. But in terms of these correlation functions, I can just take my 2 torus. So I'm going to take a T2 and I'm going to wrap both of the cycles by lines labeled by different group elements. And I want to be able to, so there'd be some 4 junction in the middle, and I can resolve it into a pair of 3 junctions. So even if there's an anomaly, as long as I'm consistent in exactly how I do that resolution, then I can just say, this picture is how I'm defining ZGH. Implicitly, I'm also inserting some weight 0 vectors at these 2 3 trivalent junctions. But for a given choice of those vectors, this will be what I'll call my partial trace, ZGH, which depends, of course, on the modular parameter tau of the torus, and that should be about all it depends on, modulo those vector choices that I talked about before. So once I have this definition, we can start, asking about properties under modular transformations. Again, if you've worked with orbifolds, this is probably somewhat familiar story. But if you want to know, say, what is ZGH at tau plus 1, well, I just draw this picture. So this is my ZGH at tau plus 1. But equivalently, I can take this fundamental domain with tau. So that would be this picture, just translating it over. And now here I can do a swap of my trivalent vertices to get back to my sort of standard form. If I have an anomaly, there will be an extra phase here, which we'll discuss later. But if there's no anomaly, then I'll just have this ZGH tau plus 1 is equal to ZG HG inverse of tau. And you can do similar tricks for all, all SL2Z transformations. I should say, please, anybody should interrupt if they have questions. I'm not going to see your hand up, I think, but I'm happy to be interrupted. All right, so now let's turn to gauging. So a network of these TDLs, so if you decorate some Riemann surface with a bunch of lines, a way you can interpret that is that it's basically describing a background gauge field for your symmetry for gamma. So it's really saying, it's essentially saying, these are the transition functions as I go from, sort of dividing my Riemann surface up into patches or something. And it's telling me exactly how I act with G as I go from patch to patch, crossing over these lines. So now that sort of hints at what we should do to gauge, of course. If we want to gauge our symmetry, we should sum over all possible background configurations. That would be, taking the orbifold of gamma. And so, for example, if we wanted to gauge it and we wanted to compute the partition function on the torus, that's saying, we should do the partition function of the torus, but sum over all possible sort of networks of lines that we could draw. And, topologically, the only networks of lines we could draw are these pictures where G and H are some commuting pair of elements in gamma. And so that's what we usually do. We say that the orbifold genus 1 partition function, Z gamma here, is given by this sum over those partial traces. So as I mentioned before, in my definition of those partial traces, I've implicitly chosen some weight 0 vectors to sit in those junctions, junctions like this, H, G. So G and H are the guys in the partial trace indices, and then the sort of middle segment there would be G inverse H inverse. So if I changed my choice of basis, so I rotated the vectors in those one-dimensional vector spaces at each of those junctions, I could rotate them by some phases, omega GH. Consistency with being able to swap trivalent vertices, of course, gives me this relation on these phases. And so that says that these phases actually live in the group cohomology H2 gamma U1. So that means they're, a cochain just is some map from G cross G to U1 in that case. This relation here is precisely the cocycle condition. And this is a well-known mathematical story, of course. So this is what we call discrete torsion. So in my language now, that's just changing what basis of vectors I'm putting in those junctions. And of course, if I were to pick a different set of phases like this, that's shifting my cocycle by a co-boundary, that would leave my partial traces invariant, it turns out, and it's basically just adding some phases associated to the lines themselves. You can think of it that way. Okay, so that says the discrete torsion choice is really an equivalence class in H2 gamma U1. All right, so given such an omega, in fact, because my partial trace had 2 junctions, I'll get 2 factors of omega. I can use the cocycle condition a little bit to massage it and write it in sort of the totally standard form. So that change of basis at my junctions just multiplies my partial trace by this factor omega G comma H divided by omega H comma G. And these are the usual place we see discrete torsion. Okay, so that's all an old story that is quite familiar. So the slight curveball I want to throw now is to consider the case where we've got a subgroup of our symmetry that actually acts trivially. Let me not say non-effectively there. Maybe let me just say trivially. I think that's more accurate. So it acts trivially on local operators, at least in the parent theory. That is, if I have a line associated to one of these trivial symmetries and I circle any local operator, it just gives me that local operator back. So if you consider the full set of symmetries that act trivially in this way, it's easy to see that, of course, if you conjugate it by something, then that thing will also act trivially. And so that means K is a normal subgroup of gamma. So you can take the quotient. That'll also be a group, G, which is gamma mod K, and they fit together in a nice little short exact sequence.
Daniel?
Yes.
Is it well defined? I mean, you can always add groups and declare that your theory has more symmetry, which acts trivial. So what does it mean that you take a subgroup which acts trivially?
Good. So yeah, I think your perspective is actually the one I prefer. So indeed, I can think of it as, I had a group G, and I'm going to extend G by some trivially acting K into a larger group gamma. Okay. Is that what you mean?
I would say the symmetry of the theory is the group which acts non-trivially. And then, okay, I can add anything I want, which will act trivially, but it's arbitrary choice.
Yes, I'll agree with that.
Let me interject for just a second. I completely agree with that description. Let me just add, for me personally, the fun part is that if you gauge even a trivially acting group, you can get something non-trivial as a result. So gauging K, even if K does nothing geometrically, actually has a meaning, as Daniel will say. Sorry, let me stop.
Yes, yeah, I'll definitely get into that in a couple examples pretty soon. But indeed, Shlomo, I completely agree. And for that reason, we're not really going to get anything new. But what I want to claim is that by considering the different ways you can extend by trivially acting subgroups, I'm going to claim that I learned something about how to think of anomalies and things like that. But mileage may vary, as one says.
Thank you.
Yeah. Thanks for the question. Right. Very good. So we've got this trivially acting subgroup now, and in the trivially acting subgroup, of course, we can have we get more weight zero states because in this case, the Hilbert space, say at the end of a line labeled by an element of K, is just isomorphic to the Baldwin-Hilbert space, and so in particular has an identity operator in it. So now the condition that your junction Hilbert space contains weight zero vectors is actually just not that the product of the lines around the junction is the identity, but it's enough that the product is actually in the subgroup K. That'll do. And so I think at the end of the talk, I'll mention how, another way of looking at it is that this gives you sort of more toys to play with, more knobs to turn. All right, so the gamma partial traces now. So gamma is this larger group with a trivially acting subgroup, or if I think of G as the true symmetry group, as was suggested.
Wait, I'm confused by that previous statement. So if you just have the element G that are acting,
yes,
and they were going to the identity elements of the non-trivial group, that's still going to be the identity element. I mean, you need to make some statement about extending to a general K.
Sorry, I'm not sure I understand. So, so first of all, these G's are elements of gamma. I probably should have called them gammas.
Yeah, so it will just go, but no, my question is an element of K is
Yes.
acting trivially.
Yes.
So how am I able to make this distinction in the theory? It's just an identity.
That's the fun part. Wait and see.
Right. So yeah, I mean, in some sense, I'm saying you can't really, you don't really make the distinction. The point is that when the group was acting effectively, only when the product was the identity would you get these topological junctions. But now, because as you say, elements of K, sort of are the identity in some more physical sense, I guess, then having the product be in K also lets you have a topological junction.
Should I think of this as taking copies of the theory labeled by
Yeah,
K?
exactly. That's a picture we're going to land on soon.
Yep.
So you're not it's not the
point.
original theory, but it's a copy of theories labeled by K.
Well, when we gauge gamma, we'll get copies of, we'll get a decomposition of our theory into a bunch of copies of things. Yeah.
So another way to think about it is that the theory in which you've gauged K has a higher form symmetry. That's a currently popular language that one can use to describe it. So in that sense, the theory in which K is gauged has different symmetries than the theory in which only G is gauged.
But that only happens because you took multiple copies and then did a different projection.
That's right.
Yes.
Okay, but it's not the original theory. I just wanted to be clear.
It's not the original theory. You are getting a different theory when you gauge K.
Okay, thank you.
Yeah. All right. So let me let's try to proceed then towards gauging this gamma. So the gamma partial traces labeled by two commuting elements of gamma, they're going to be related to the G partial traces. Now I'm going to make a naive assumption to start, which we will relax later. My naive assumption is just that, under this sequence, I can map elements of gamma to G, and since the elements of K are supposed to be trivially acting, then it's reasonable to make a guess like this, that the gamma partial traces are really just equal to the G partial traces if I project down the indices. So now if I take the gamma partition function, that would be this thing. Epsilon is, maybe I could include some discrete torsion. then I can rewrite this as a sum of G partial traces. You get some sum like this, where I'm basically just breaking up my gammas into other things. And so I'll get, for each G and H and G, I'll just sum over all the sort of K, everything in gamma that's related to those by multiplying by elements of K. And, in general, the sum's a little tricky, but you would get some factors like this. If you compute these things for fixed G and H, you'll get some coefficients that will sit in front of these G partial traces. So let's work towards doing some examples of that. So this story, by the way, and what we'll see is that this result then assembles into essentially a bunch of copies of theories, which are orbifolds by either G or subgroups of G. That's the picture we're going to land on. And so that story is known as decomposition, and it's an old story Eric and others have worked on for many years. All right, so as a first example, I'm going to consider when the whole group acts trivially. So this is also known as the orbifold of a point, because you can't really do anything interesting to a point. So, well, except maybe you do find this interesting. So we're going to take the whole group to act trivially. In that case, every twisted sector is just isomorphic to the original apparent theory twisted sector. And for every operator in the original theory, that'll map, there will be an isomorphism that maps it to some operator in one of these twisted sectors. If we don't turn on discrete torsion, then we can figure out that the gamma partition function is just n copies of the original parent theory partition function. So here, this is a trivial group in the top there, and that really just means Z111 is just the original partition function, the trace over H itself. And this factor n, if we apply the formula on the previous page, we get this. And this is actually just the number of conjugacy classes of our group K, or K being also gamma in this case. So I'm going to call that, I'm going to relate that to something I'm going to call K hat. K hat is going to be the set of isomorphism classes of irreducible representations of K. And it's a well-known fact that the number of elements in that set, the number of isomorphism classes for a finite group, is equal to the number of conjugacy classes. All right. So for example, if K is abelian, then it's just a bunch of single element conjugacy classes. So n there is just the order of K, and you get K copies of your parent theory. So your copies are labeled by the group elements. Your symmetry just shuffles you between copies, as we were saying. And so that's just what you get. If K is non-abelian.
Sorry, Daniel, all this story is only for discrete groups? For
that's right, yeah.
Finite groups?
Very good. In this talk, I'm focusing on finite groups. Yes, sorry, I should have said that much earlier. I think some of it generalizes, but we haven't given it a lot of thought here.
All right, what sort of representations do you wish to entertain? Are they going to be unitary, or will you allow projective representations, things like this?
Here I'm just ordinary, group theoretic complex representations.
So you require it to be matrices in GLV or action in GLV.
Exactly,
You won't allow PGLV?
Not yet. Good. So
it will appear later.
That will play a role later, actually. But right now, okay, it's just ordinary representations, not projective ones.
So we lose no generality by taking the standard irreps?
Yes, exactly. Yeah.
Okay. Okay. Thank you.
Mm-hmm. So if K is not abelian, then what we have to do is count commuting pairs. So for instance, if you do S3, well, the identity commutes with everything. So that gives you 6 pairs if the first element's the identity. If you have a 2 cycle, then that only commutes with itself in the identity. And if you have a 3 cycle, it only commutes with this. So altogether, there's 18 commuting pairs. And so the S3 orbifold in this case gives you, 1/6 times 18 times the original partition function. So you just get 3, the number of conjugacy classes. Okay, everything's working. So as a first generalization now, let's try to add discrete torsion to this story. So for example, I can take K as Z2 cross Z2. So that has the option to turn on some of this discrete torsion. So the non-trivial element in that case gives phases that just flip the sign of the partial traces where the two indices are both not the identity and not equal to each other. So all of those partial traces get their sign flipped and the others don't. And so if you compute the partition function now, in this sum, you get 10 terms with a +1 and 6 terms with a -1, which gives you 4. You get a 1/4 out front from the order of the group. And so you just get the parent theory by itself. And so this shows that, even though I am extending my symmetry by something that acts trivially, I don't always get copies. So without discrete torsion, I got a bunch of copies. I got the number of conjugacy classes. But here now with discrete torsion, in this particular example, I don't get multiple copies. I just get the original theory back on the nose. So that's already, I think, a little bit interesting. So in general, now let's go to a more general story. It's going to be pretty similar. So now what will happen is when I turn on discrete torsion in gamma, the answer is not going to be anymore just the number of ordinary irreps. What I need to do, in fact, is pull omega back to K, or restrict omega to K, and then look at the representations of K that are projective with respect to I star omega. So yeah, let me try to go through that. So, and then, so I need to count the number of those projective irreps, and that'll tell me how many copies I get in this theory where everything acts trivially. So let me go through that in the Z2 cross Z2 case as well. So first of all, just a definition, I say that a representation of K is, well, an omega projective representation of K, where omega is some 2 cocycle on K, is basically just a vector space V and a map rho from K to GLV. But rho is not going to be a homomorphism now. It's going to be a projective representation. So these omegas are phases, and they only satisfy the group multiplication law up to those phases. Now, if you just try to define this without, for any group, you can try to define such things, and you can ask, do any phases work? The answer is not quite. There's consistency conditions. So for instance, these rows are really should just be matrices. Matrix multiplication is associative, and that puts a condition on these omegas, turns out to be exactly the cocycle condition. Omega has to be co-closed. Conversely, given any co-closed omega, you can look for representations that are projective in this sense, and you can always find them. You can always construct such representations. There's a construction analogous to the regular representation that you can do. And you can, again, define irreducible in the usual sense and isomorphic in the usual sense, and look for isomorphism classes of irreducible projective representations. One extra fact, well, so actually let me just go for Z2 cross Z2. So if I take that non-trivial discrete torsion choice or non-trivial 2 cocycle, again, sorry, I gave you the discrete torsion phases before. The corresponding 2 cocycle has I or minus I. Up to isomorphism, the only projective irreducible representation turns out to be something like this, where basically you're just mapping things to the Pauli matrices. So that's a nice fact about Z2 cross Z2 that you can prove. And note that, so this is the only projective irrep, and it's 2-dimensional. It is in fact a general statement that if the cocycle is non-trivial in H2, then you don't get any 1-dimensional projective irreps. You only get higher dimensional ones. So that'll play a role down the line. Okay, so we basically exhausted the story that we can tell for the case where the whole group acts trivially. But now it turns out the structure again gets a bunch richer if we look at the case where just a subgroup acts trivially. So it should again be true, Z gamma should now decompose into orbifolds, as we were discussing before, orbifolds by subgroups of G, where G is gamma mod K. So again, our example where we extend Z2 trivially up to Z2 cross Z2. If we don't turn on discrete torsion and we compute the Z2 cross Z2 orbifold, we just get 4 copies of each of the G partial traces. And so this just gives us 4 copies of the Z2 orbifold. That was the story without discrete torsion that I reviewed before. 4 disjoint copies in some sense, with a one-form symmetry that swaps them around. If you do turn on the discrete torsion, however, in Z2 cross Z2, and now only at one of the Z2s acts trivially, so what you get is you again get, the guys that reduce to the identity partial, the 1-1 partial trace in G all come with a plus sign, but the ones that reduce to the non-trivial partial traces in G come with, of the 4 copies, 2 of them come with plus and 2 come with minus. So these minuses are the 6 terms from the gamma partial trace that got minus signs from the discrete torsion. And they all now cancel out exactly. And so again, we just get 1 copy of the parent theory. That was the story we did before. Well, actually slightly different now. So here we still get 1 copy of the parent theory, even though it's not the whole group acting trivial. All right, so a more complicated example, you can go to, start with Z2 cross Z2 and extend it up to the dihedral group of order 8. So that dihedral group has a discrete torsion you could in principle turn on. And if you go through the exercise again, just like we've been doing, what you find is that if you don't turn on discrete torsion, you get 2 copies of the Z2 of a Z2 cross Z2 orbifold. But it turns out those 2 copies in that case are not identical. One of them has discrete torsion turned on and one does not. So that was an old story. Now you can ask, well, what if I turn on discrete torsion up here in D4? That's a question that hadn't been asked before. In that case, you find that the whole partition function just gives you 1 copy of a Z2 orbifold, Z2 subgroup of G. Right, okay. Very good. Let's do one more example. So if I take S4, that's got an interesting normal subgroup of Z2 cross Z2 that I can declare acts trivially. In that case, the sort of real symmetries, the one that's, gamma mod K, is just S3. S4, again, has a discrete torsion you can turn on. That's a computation that can be done. If you don't turn on the discrete torsion and you do this decomposition story, you get 2 disjoint theories. One is the parent theory and one is the S3 orbifold. If you do turn on the discrete torsion up in S4, the only term you get is the S3 orbifold. So just, there's a bunch of copies. All of these, once I've shown you how to do it with an explicit case like the Z2 cross Z2 up here, it just goes the same way for all of them. It's easy to just play this game and generate a bunch of examples, and that we did. But we can now actually give sort of an algorithm to get the answer in general. So this is a bit conjectural. It works in all the examples we've checked, and it passes a bunch of consistency checks, but we haven't actually proven that it's always correct. So here, the given data is you've got some extension, short exact sequence. So you extend G by a trivially acting K to some group gamma. I'm going to need to label my maps, inclusion of K into gamma and projection of gamma down to G. And I'm also going to need to pick a section, lifting G back up to gamma. Nothing will depend on the choice of section as usual, but I need to give it a name in order to state certain things. And we're going to pick a choice of discrete torsion inside in the gamma. And so now we're going to ask what happens when you gauge this gamma. Well, step one is pull back omega to k and find the set of irreducible projective representations of k with respect to I star omega. Now, the next step we're going to have to do is we're going to have to actually construct a G action on that set. That can be done. It takes a little bit of work. So what you do is if phi is some projective irrep and S is my section, then sort of in the case where we didn't have discrete torsion, there was a construction like this where you basically just apply phi to the action. You know, this is G dot phi on K would naturally be phi of G inverse acting on K, and G inverse would act on K just by conjugation. And so without these omega factors, that's what you would normally have. Here, basically, we're going to need to include some omega factors, and I'll say why in a moment. But then this defines some LG phi, and basically these omega factors were picked so that LG phi is also projective with respect to the same omega. If I didn't include these omega factors, I would have gotten it projective with respect to a different cocycle that differed from omega by a coboundary, but I can basically undo that coboundary shift with these prefactors here. Okay, so that, given a phi, it now gives me LG phi as another projective representation. It turns out this is not actually a good group action on projective representations because LG1, LG2 is not equal to LG1, G2, but they're isomorphic as representations, as projective representations. And so this does give lift to a good group action on K hat I star omega, the set of isomorphism classes of projective irreps. All right, so now that you have a G action on this set, you can decompose it into orbits. In each orbit, you can pick some representative. So rho A here is a projective representation. The square brackets means it's isomorphism class. And then you can find the stabilizer of that orbit, basically, of that representative. And so every orbit that you take is going to lead to a copy in the final set of things. So that copy will be an orbifold by GA. And in general, there will be some discrete torsion turned on. I'm not going to give you the rule for that. Basically, from this LG phi, you can sort of lift it to a representation on gamma that is also projective. And from the cocycle, from that representation, you can extract a discrete torsion. But basically, there's some explicit concrete calculation you can do to get the discrete torsion in each copy as well. So you can see our papers for details of that. And that's the rule. So in the Z2 cross Z2 case, for instance, there was just one projective irrep. So there's obviously only one orbit. The G action on it had to be trivial, and it was. And the stabilizer of that guy is, sorry. Yeah, it works. It all works very nicely. So this algorithm works in all examples we checked. I think that's what I wanted to say. Yeah, sorry. The example I did before wasn't quite of this form because K wasn't Z2 cross Z2, but if I did an example like that, it works as well. All right, so that was the first of the papers this year, was introducing that generalization of the decomposition story to add in this possibility to discrete torsion. And one of the consequences was you don't always get multiple copies, you might just get one copy of your theory. All right.
Is it unique?
Now I want to turn to talk about anomalies. Oh yeah, go ahead.
Is this G action you constructed, is it unique or are there different choices?
That's a great question.
So if I may, the algorithm is completely predictive. There may be different presentations. You may be able to get the same result by playing different games. Just as a dumb example, if I start with a G and I pretend that it's acts effectively and extend it by K, but then later on, maybe I discover G itself has a further trivially acting subgroup. I mean, there are various interlocking games you can play, but the algorithm Daniel has outlined is completely projective. You specify a gamma and an element of discrete torsion, and this gives you a precise formula for all the constituent orbifolds as well as the discrete torsion on each of those pieces. Yeah.
Sure, I understand, but I have choices at some of the steps. That's part of it.
That's right.
The choices don't matter. So for example, I think at some point Daniel mentioned a choice of section. That doesn't enter, the choice of section cancels out by the time you get to the end. So there are various choices you have to make at intermediate steps, but none of them change the final result.
Yeah, I believe.
Well, wait, what if I had taken the trivial extension and taken the trivial group action?
Well, the trivial extension,
Yeah, that's fine. So in that case, the group action's trivial.
okay, but then you have a different gamma. So for a fixed gamma, so if you start with a fixed gamma and a fixed G and a fixed K, and a fixed omega in degree 2 cohomology of gamma, that gives a unique prediction for the result. The choice of section is arbitrary. So the choice of section enters that formula for the left action.
Yes, I
Change
understand
the
that part. Okay, got it. Yeah.
Yeah.
Okay, thanks.
Is the end of the day is this is turning on some non-trivial background valued in K for the theory that you started with?
Not really. This really is gauging a trivial group action. It's basically, this is an example of introducing these are all games in theories with higher form symmetries. And I don't really know how to understand a higher form symmetry in general as as giving a VEB to an ordinary background gauge field. I wouldn't.
No. Let's okay. So let's say it another way. So when you said G acts trivially, do you mean acts trivially on local operators?
Yeah.
Or do you mean so? Good. So then you can have a subgroup of G, let's say the center symmetry, for example, which can act non-trivially on lines and other stuff as a high form symmetry.
And
so
it pops up. So for example, D-branes. We could talk about D-branes in these cases. If you have a D-brane in that gamma orbifold, to specify the D-brane, we have to specify an action of gamma, not just G, which means we have to specify an action of K.
So then if you, sorry, let me just finish my question along this line. So then if you take K and you turn on, and you gauge in K, shouldn't that be thought of as just turning on some, for example, non-trivial lines, which you can also think of as turning on?
Right, gauging K is summing over all background configurations for K.
Yeah, which can be also thought about as turning on a line can be mapped to turning on a non-trivial background valued in the group.
That I completely agree with, yeah.
So in the end, what you say you're doing, you have group G and you take a subgroup and you sort of turn on backgrounds for that. I guess that would be the statement.
No, so there's two different ways that you can think of it. You can say, I've got a group gamma that includes a trivially acting subgroup, and then I'm gauging gamma. So I'm any configuration of gamma lines is equivalent to a background gauge field. And if I want to gauge it, then I should sum over all such configurations. The other way of looking at it is I've got a symmetry G, and I'm going to extend it by sort of declaring that I have these extra trivially acting lines. But act trivially on local operators. And thinking carefully about how they act on non-local things, that's going to play a role at the end of the talk. But again, any kind of insertion of lines is, as you say, essentially equivalent to turning on a background gauge field. Yes.
Okay, good. So that was the question. So in a sense, when you said gamma acts trivially, you just meant acts trivially on local operators, and then you're just trying to understand the global structure for this gauge group and how should you piece out the different components, the different sort of sectors of the theory that you would get by turning on these non-trivial background. And in a sense, you're picking a global structure for the gauge group.
Yeah, essentially, I agree with that. Yeah.
Thank you.
Okay, so yeah.
Sorry, before you go on,
yeah, sure.
a different question about this bit. A stupider question. So could you Did you actually need the new point of view with defect lines and all this, or could you?
Not yet for this part, really. Yeah. So the defect lines will play a larger role in.
So this part of of your work could have been done many years ago.
Yes. Yeah. That's right. In some sense, adding in discrete torsion to this decomposition story, I think could have been done indeed.
Because just that the new point of view reinvigorated the field, and so you decided to.
Well, so yeah, so I'm telling things a little bit out of order. So I'm gonna, with anomalies now, I'm gonna kind of, yeah. So let me if you still have questions at the end, bug me again. Yeah. So anomalies play into a role into this story. So in terms of lines, that's I think a nice way to understand how the anomalies work. Basically, this picture and this picture no longer have to be equal, for at least for a given choice of basis vectors. They could differ by a phase. So the way I like to think of it is that this is sort of an analog of OPEs, right? In an OPE, if you've got some local operators, here and here, you can draw a circle around them, and that should be equivalent to having just a local operator inside the circle, just because whatever happens inside the circle, you can encode into a state on the circle, and by the state operator map, that's equivalent to a local operator inside. So in our situation here, again, the same kind of thing. I could draw a circle around this. All I know is that I've got these 4 lines coming out. And so that has to be equivalent to some picture where I've just got a 4-valent vertex. If I have topological vectors at my junctions, then that 4-valent vertex would also need to have a topological vector. But I could have played the same game. And so since the topological vectors, vector spaces are one-dimensional, if I pick a basis, then basically this picture can just be, related to a phase. But this picture can also be related to just a phase if I reduce it to a 4-valent vertex, but it might not be the same phase. So these pictures may differ just by a phase. Now, because we're restricting to topological cases, that means the product of the 4 lines around that circle has to be the identity. If I'm in the effective case, this is the usual story. These are G lines, not gamma lines. So that means the 4th one is just fixed in terms of the first 3. And so that phase is really a map from G cross G cross G into U1, or in other words, it's a 3 co-chain. Then you can play the usual sorts of games that people drawing these pictures play. You can, there's a pentagon identity, where if you've got 5 incoming lines, you can, sort of do a cyclic shift around them and end up back at the same picture you started with, but you find that you get 5 factors of omega or omega inverse. And so that product has to equal 1. And that is precisely the condition that omega is actually a co-cycle. Similarly, if I change my basis vectors at my trivalent junctions, you find that omega shifts by something in terms of 2 cochains. And it turns out to shift exactly by the co-boundary of those 2 cochains. And so that part is should be inessential. And so we find that the anomalies, in these phases relating these 2 pictures are basically classified by H3 GU1. That's our usual story. And so if you go back to this picture I had here, where I did the modular transformations for these partial traces, in this last step down here, when I do this trivalence exchange, I'm going to get a phase. Okay, so my modular transformations are not really going to close the way I expect them to anymore. And so you can see this very easily in nice clean examples. Take G as Z2. That admits the possibility of an anomaly. H3 Z2 U1 turns out to be Z2. And so if you've got a symmetry that has that anomaly, what you find is that, although you can, build these partial traces, you can just define them like this, but they won't, sort of the modular invariants won't really obey the group law. So I would have wanted this to be Z1, 2. And if if 2 is the same as 0, if I really had a Z2, that should have been equal to Z10 with a plus sign, but it wasn't. So one way of sort of, this failure here has, is also a venerable story. So this happens often in asymmetric orbifolds. So one, sort of I would say the simplest example I know where this will show up is if you take just a compact boson, and if you do a translation that is a mixture, sorry, if you do a symmetry that's a mixture of sort of a translation and a dual translation, you can pick such a guy that is order 2, but you find that this happens. What we say is that that element is anomalous. So there's a mixed anomaly in the free boson between the ordinary and dual translations, if you like. And so you can just compute these partial traces and see that this is true. In the old literature, this is called a failure of level matching. We say that this orbifold doesn't lead to a modular invariant partition function. And I think the point of view in a lot of the old literature is just that, okay, we need to just discard it. Another way of saying it is that that symmetry was anomalous, right? We shouldn't gauge anomalous symmetries, and so we shouldn't have been trying to construct this orbifold partition function anyway. I can still define these partial traces by this sort of diagram, and then it's just they satisfy this, and so I can't build my orbifold partition function in the usual way. But there's sort of a resolution here, inspired by this whole decomposition story, which is that, well, I can just say what's actually happening is that I didn't have a Z2. I thought it was a Z2, but actually it was a Z4. And the Z2 subgroup of Z4 just acted trivially. So I didn't see it in terms of the physical symmetries on my original theory, but that's fine. And indeed, so if you look at this extension, you can pull the anomaly back to Z4 and you find that it's actually trivial. So Z4, perfectly well defined, not anomalous. You can gauge by it. So what's happening here is that this Z12, I just define it essentially in terms of modular transformation, Z10 of tau plus 2. And it happens to equal minus Z10. But then if I just construct my Z4 partition function, I get a bunch of cancellations and I end up with just the parent theory. So basically I'm saying, you bring me this symmetry and you say it's anomalous, so you can't gauge it. And I say, the hell I can't gauge it. I'm extending it by something trivial, and then it's non-anomalous, and I'll gauge that. But of course, at the end of the day, there's no, I'm not getting anything new. I'm just getting the original parent theory because I didn't have any non-anomalous symmetries, so there was no way I could get anything else. And in fact, so this story was what inspired Thomas and I in the first of those papers I listed. We were trying to think about asymmetric orbifolds, and we had this picture. If you're not working just with some simple free field situation, then it can be really annoying to try to construct all those twisted sectors, and then check level matching and so on and so forth. But in many cases, you can just use the modular transformations. You can start with the untwisted sector partial traces, which you can just get as actual traces over Hilbert space, and then just start generating things with modular transformations. If there's discrete torsion, this doesn't work because there are orbits, there are partial traces you'll never get this way, orbits that are disconnected from the untwisted sector. But if there's no there's no discrete torsion possibility, if H2 is trivial, then you can, in principle, sort of generate everything at the risk of possibly enlarging your group. In fact, to put it very sort of a bit more explicitly, if the group, if it's a cyclic group, formally, if you lift it to the integers have H2 and H3 are both trivial. And so there's no discrete torsion, there's no possible anomaly. And so you can always kind of just say, I'm just going to lift my symmetry to the integers and declare that a bunch of them act trivially, and do try to gauge that integer symmetry. And you get an infinite number of copies, but then you realize that in fact you can just extend it by a finite symmetry and do the same thing. And this always works, but it never gives anything really new. At the end of the day, you always get something that's either the parent theory or gauging some non-anomalous subgroup of G. So what was the magic sauce that let us do this at the end of the day completely uninteresting thing? Well, it's because we relaxed that assumption before that the gamma partial traces were just equal to the G partial traces. Now there's an extra phase here. And I'm calling it epsilon again, but it's not the same as discrete torsion in general. This is a different sort of thing. So you can ask, how general can these phases be? It turns out that they're basically determined by an element in, well, essentially H1G, H1KU1. Now that's a messy thing, but let's say if we restrict to central extensions, which I think I mostly will be through this discussion, then H1KU1 is just sort of the Poincare dual of K. It's just isomorphic to K. And so that's a nice simple situation. And then those phases are basically just the ratio of two B's, very similar to how the discrete torsion phases are a ratio of omegas. So here, I've taken a decomposition of any element in gamma. I've written it as basically something in G and something in K. That requires a choice of section, but you can do it. And then you can define your phases this way. And again, as usual, you can check that the choice of section doesn't matter and the usual sorts of things. So in particular, if you just focus, so this was a relation, this was phrased as a relation between gamma partial traces and G partial traces, but that also implies a relation between gamma partial traces. And in particular, if I just take, say, the G twisted sector and the action of HK, that's going to be the same as the trace I got from the G twisted sector with an action of H with this phase B inserted. And so that's telling us basically we want to interpret that as saying that although K acts trivially on the parent theory, it acts by phases on G twisted sectors. And remember, in terms of the parent theory, you could find the G twisted sectors as the guys at the end of lines. And so that's also telling you that K, this trivially acting K, is now being taken to act non-trivially on lines. So we call these quantum symmetry phases. They're not quite the same as the quantum symmetries that are in the old literature, which are basically related to discrete, well, quantum symmetries in the old literature. It's a bit of a different thing, but these ones are only present when you have a trivially acting subgroup. You need both K and G to be non-trivial in order to get something interesting here, but in those cases you can get them. So just have a couple more slides here. So these phases, so let me just talk a little bit about some math. There's something called the Linden Hotshield Sare spectral sequence. So this is a spectral sequence that's sort of designed to help you compute group cohomology of group extensions. So if you want to compute the group cohomology groups of gamma in terms of the ones from G and K, there's a spectral sequence type construction. In principle, lets you do that. In practice, is pretty horrible to use. But one of the ingredients in it is that you have a nice map D2, which takes you from those group classifying or quantum symmetry phases into the group classifying anomalies in G. That's kind of cute. And in fact, there's also a map. If you're in the kernel of this D2, then it turns out there's another map that sends you into the discrete torsion phase, group for gamma. So, and that second map is actually injective. So what that's saying is, first of all, if B is in the kernel of D2, then B can be essentially made equivalent to just a choice of discrete torsion and gamma. But the interesting thing is when B is not in the kernel of D2, in that case, D2 of B is some possible anomaly in G. And if you pick a B that actually maps to a given anomaly, there's also, that will only work if the anomaly lifted to something trivial. So if you're in the image of D2, then it's an anomaly that is sort of resolved by a given extension.
I'm not sure if I'm the only one having problems.
Yes, I also don't hear.
Yeah, I don't hear him.
I'm back
Muted.
now. Sorry.
I think he's back.
I have my apologies. Let me share screen
I thought it
again.
was my connection.
Sorry about that. Right. So if you pick a B that maps by D2 into the anomaly that got resolved, then things work. You can play the same games we had before. You can do decomposition with these symmetry phases. And there we have also a conjectured algorithm. I'm not going to go through the details. It's sort of a little less unified than the one we had for discrete torsion, but again, it seems to work in all examples. But finally, I also want to say maybe one more point here. Even when it's just discrete torsion, it turns out we can still resolve an anomaly. And this will sound a little weird and may bother some people, but hear me out. So suppose G is anomalous. So let me take this example where my Z2 is anomalous, and I'm going to extend it just with a trivial extension. So I just have a K, and my extension is just Z2 cross Z2. So if I pull back the anomaly from here, it will be an anomaly in gamma. So gamma is anomalous, and conventional wisdom is I should not be able to quotient by it. However, if I turned on discrete torsion in gamma, which in this case is equivalent to turning on one of these quantum phases for some choice of quantum phase, we already saw that, for this trivially, because K is trivially acting, what you get is just equivalent to the parent theory itself, not the G orbifold, just the original parent theory. And that, so the end result that the decomposition predicts is not an attempt to take an orbifold by an anomalous group. And so you could ask, well, maybe it was okay. And indeed, that's something we're sort of thinking about now. Basically, what happens is that because you've got this trivially acting subgroup, because you've got more junctions where you could put topological vectors, it turns out that there's a way of doing your gauging, even though gamma was anomalous. So you can kind of sidestep the anomaly by picking some, the vectors where these, lines join up by picking them appropriately. So that's sort of work in progress. And so I think I will more or less just end it there, I guess, and ask if there are any more questions, since I'm a bit over time. Thank you.
Thank you. Let's thank virtual or otherwise Daniel for the very nice talk. And any further questions?
I might have missed it, but
Yeah, go ahead.
I might have missed it, but is there like a 3D TQFT you can talk about in this context that characterizes the anomalies or not?
I think so. So yeah, so you're talking about just sort of extending the 2D CFT to with a 3D TFT to classify the anomalies. I think so, but I haven't given that a lot of thought yet. There should be a picture like that, but I don't know how it interfaces with the trivially acting subgroup story.
Mm-hmm.
Let me just add a word or two. There is a procedure in the literature due to Wang, Witten, and Tachikawa, and Daniel and Thomas may well correct my references, that extends to higher dimensions. So formally, just at a mathematical level, you can extend to a gamma and then play some games to resolve the anomaly. The details of this particular story, the decomposition in particular, are specific to 2 dimensions. I don't expect a decomposition to work in 3 or more dimensions, basically because the higher form symmetry is wrong. But yeah.
But I think that's not, that might be slightly different than what John was asking about.
Yeah, maybe I misunderstood your question, John. Sorry about that.
I mean, there's a usual lore that you talk about the anomalies in terms of like a 1 higher dimensional TQFT. Yeah. So I'm still talking about your 2D system.
Yeah.
Sorry,
I just want to understand better what the anomalies are. And so
yeah, and so there absolutely should be a story there, and we haven't worked it out yet. So I think that would be quite interesting. Yeah. And actually Eric's reminded me, so I was really bad with giving references throughout this talk, but so in addition to, learning about the TDLs from Chang et al., there was this Wang Wen Witten paper that sort of had similar ideas about extending groups to trivialize anomalies. And there was also work by Bardwaj Tachikawa and by Tachikawa solo that did a lot of other similar sorts of things about resolving anomalies that we are, inspired us, basically.
Can I ask another question, or is that not?
Yeah, please. Go ahead.
What about supersymmetric systems? Is it a completely independent story or not? It's not clear to me that it is.
With the caveat that I haven't really given that any thought, basically, I think it should be just orthogonal. I think this is just a story about CFT, and the S wouldn't change much, but
yeah, I agree. I would expect supersymmetry to just go along for the ride unless you were doing something particularly obscure.
Yeah, there might be an interesting story where you look at trivially acting fermionic symmetries or something. I don't know, but yeah, that probably doesn't make sense. All right.
So in this what you showed us in this last slide, this is really a way to resolve an anomaly. It's not a accounting trick or a sleight of hand. I mean,
Yeah. So okay, good. So
what's going on physically? I mean, can you how?
Yeah,
why?
great. So a version. Yeah. Let me. So one story that I didn't really have the time to go into is this, there's this very nice picture in the language of TDLs for how you should think about the gauging. And what you do there is you take your collection of topological defect lines and you try to construct what is sometimes called an algebra object. So this is a line. So in the usual story, what you do is you take the sum of all the direct sum of lines corresponding to all your group elements. So you can think of that as basically a projection operator onto invariant states. But it'll be some line, so some, A, basically like this, and then you insert A. So on any Riemann surface for any correlation function, to get the correlation function in the gauge theory, you just take a sufficiently fine kind of triangulation or something of A and just of the Riemann surface and put A on every line everywhere. And you want this to be sort of consistent. So you need A to sort of be able to resolve nicely in the standard way. And A has to kind of act as a projection operator. So if you take A with itself, you should just get A back. And in this language, once you choose A and you choose your vectors at all your junctions of A lines, then to gauge the theory, you just put A everywhere you can. And so in particular, to compute the torus partition function, that's exactly what we were doing. It's just we decomposed it into all the pieces in this sum. Those were the different sums in our, those are all the different ZGHs. And that's exactly what we were doing. So a key ingredient in that is, choosing the vectors that go, the topological vectors that go at these junctions. And, for an A like this guy, if the symmetry acts effectively, there's not a lot you can do at those junctions. It's basically, but that's where discrete torsion goes, for instance, is you can encode the discrete torsion in those junction vectors. But what happens when you've got a trivially acting subgroup is that now these junction vector spaces are much larger. There are many more combinations of pieces of A that give you the possibility for topological junction vectors. And so what I believe is going to be the case, but we haven't really worked out the details yet, is that in a case like this, where we have this anomalous Z2 cross Z2, because of the trivially acting subgroup, I can pick an algebra object that sort of sidesteps the anomaly, even though it's a sum of all the different lines.
Well, it's a generalization of the usual idea of orbifolding.
That's right. It's still, yeah, it's still very much the usual kind of gauge procedure in at least in this language of it. You just pick an algebra object and then go from there. It's just that now we have a larger choice of algebra objects to pull from because of the trivially acting. And that's where this trick is really hiding.
Cool.
All right. Oh, thanks very much for the invitation.
By the way, so perhaps I can now stop the recording and we can maybe wait a second to see if the